Thanks. Let's see, I got to make sure that we're actually recording. Down there. Yeah, okay, good. All right, last time we left off, we were on that slide of problems with starts. There we go. We had covered a no start, and of course slow acceleration. That would be a great test question. What would be the possible outcomes during an engine start if the engine accelerated slower than normal? One outcome is it could turn into a hot start, and then the other outcome is that it could turn into a hung start. So there's another good question. What do you do in case of a hot start? Number one, fuel, what goes off? What kind of fuel? The nozzles get turned off, and then, I know it was yesterday, motor the engine if possible, and we're going to get to why it's if. Right there. Definition of a hot start, we covered that. Definition of a hung start, we covered that. You can expect one or both of those on the test. And then what do you do in case of a hung start? It's exactly the same as, yeah, so if I say, what do you do in case of a hung start, don't write down the same thing as a hot start. I'll be very specific. I'll say, what are the two steps you must take as the operator of a turbine engine if you have a hung start. So hopefully, and torching. So we didn't get to torching. When in doubt, do not take an acetylene torch to a jet engine. It won't let me erase it. Oh, I saved it. Okay, all right. Well, torching is when flames come out of the back of the engine when it's running, including during start. So torching is generally caused by something going on inside of the combustion chamber that's not normal. Maybe it took an extra second or two or three for the ignition to catch the fuel on fire. So maybe some of the fuel caught on fire, but it came out and went through the turbine section as a liquid with the liquid on fire and actually came out. The fuel was still burning. So torching is when you see flames coming out of the exhaust pipe. And it could occur start. Now, if it's a little bit up and it doesn't happen during the next engine start, you really don't have to worry anything about it. If you're seeing torching all the time, every time that engine starts, now you need to do something about it. And so you as a jet engine mechanic are going to get to try to figure that out. The ignition comes on when it's supposed to. Is the fuel control squirting in more fuel into the engine than it was designed for during start? What's the EGT during start when you see torching? Maybe the EGT is a little higher than normal, but it didn't hit red line. For instance, we've been running that APU tab. Everybody's going to get a chance to start it once between a couple of days ago and the last day of classes on Friday. And when the engine is cold and you start it up, it was going up to 800 and some degrees Fahrenheit. And if it was hot, because it had already been run, and you started it, I was seeing 960 degrees Fahrenheit. The line for that engine is 1300 Fahrenheit during engine start. So we were more than 300 degrees Fahrenheit colder than the red line. But if I saw torching and I was looking at the EGT gauge and it said 1200, aha, it's hotter than normal and fuel is burning while it's leaving the engine to the point I can see flames, that's going to be a pretty good clue that, well, something's wrong, but why would you have a higher than normal EGT and have torching? Excess fuel during the starting sequence. So the first place I'm looking is, I'd say, did the ignition catch fuel on fire when it was supposed to? And if it was, how much fuel is getting squirted into the engine? So that would be going, okay, maybe I need to be looking at the fuel flow gauge during the engine start, or I was looking at the fuel flow gauge, and instead of 500 pounds a minute, it was 700 pounds a minute. Now I'm going to have a pretty good clue that it's the fuel control. It is putting more fuel into the engine than it's designed for. All right, the two major types of starter motors that you're going to find on 99.9% of engines out there, if you're not working on military jets, is either going to be a starter generator or a pneumatic starter. Starter generators, they're all going to be 24/28 volt systems. And a starter generator is what's on the PT6 out in the lab, the one on the stand with the propeller on it. And during start, you give it electricity, and it converts electrical power into rotational power, and it spins the engine. After you get the engine started, you flip a switch or two, it turns it into a generator, and now it takes energy off of the engine and converts it into electrical power. So it does both of these two things. It's a starter and it's a generator, hence the term starter generators. You like how I fit the word hence in there? No? Brian's saying no. He's going. In any case, I've never seen a starter generator on a turbine engine that was a 12-volt/14 volt system. Never. I've only seen them on 24/28 volt systems. And if the engine is small enough to have a starter generator, then pretty much it means that there's a battery on board the aircraft that will power the starter generator during start. Because the weight of the battery, and the weight of the electrical cables, and the weight of the starter/generator is small enough that it weighs less than if you put an APU on and fired up the APU. Except for the APU, I've never seen an APU on a turbine-powered aircraft that was a civil aircraft where the APU didn't use 28 volts DC to start it up. I've seen some APUs that the starter wasn't a starter generator, but the starter had 28 volts. Pneumatic starters, of course, they use power off of the pneumatic system. High velocity, high volume, high pressure air. It's probably going to be hot. Of course, if we're going to use it to start an engine, we don't really care how hot it is, but we'll need that high volume and we'll need that high pressure. And you're generally going to find pneumatic starters where the engine is so big that the weight of an electrical starter generator and the weight of a battery and the cables to go out through the wings to get to the engines and all of that weighs noticeably more than the weight of an APU. Because those bleed air ducts, you're running a lot of them around the airplane anyway, and they're thin, made out of stainless steel, so they don't weigh much, even though they might be 3 inches in diameter. When the weight of that APU is less than how much a starter motor and a battery would weigh, that's when an engineer decided to put an APU and pneumatic starters on the engines. So except for one amazingly interesting exception, you're going to find that big old honking jet engines, big business jets, and you don't have to write that down, but big business jets, big helicopters, big turboprops, and transport category jets, airliners, they all have pneumatic starters because the weight of the pneumatic starter on all the engines added together and the weight of the stainless steel ducting and the weight of the APU is less than the weight of a battery. Think about how big will a battery have to be to start a 747 engine? How many pounds? Yeah, it would weigh like 400 pounds, and that's almost as much as I weigh. So, and that's just enough to start one engine. So we're going to take a look at starter generators. Effectively, you're going to see generators put on aircraft where the primary power is 28 volts DC direct current. That means the electrons only go one way through the majority of the components. So if it's a 28 volt DC system, and that's what all of the electrical components on the aircraft operate on, and it's a turbine engine, you're going to have a starter generator. The battery is going to be big enough to start the engine. So generally it's smaller engines, and of course I already said it's a DC starter motor during start. You may notice this looks very similar to the starter generator that's on the PT6. Everybody's going to get to take a peek at that. Whoops, why did that disappear? Oh, pushing the wrong button. And there's 2 places you can get electrical power to run this DC starter generator. You can get it off of the battery that's on board the aircraft, or you can get it off of a ground power unit. We're actually using a ground power unit out at the engine block, at the engine run-up stand, to provide a very high amperage, 28 volts DC. So you could use that same power unit and plug it into an aircraft and start an aircraft engine if it had a starter generator on And of course, you start it up, I already said, after you start it up, you flip a switch or two, it stops being a starter motor, starts being a generator. And that saves you a little bit of weight. You don't have to have one starter and one generator. So that makes up for the fact that starter and because now this one thing, it's about 10% heavier than a starter or 10% heavier than a generator, but it does the work of 200%. Now, here's what's really important about starter generators, is that starter generators are always connected to the engine. For instance, this shaft that's sticking out. So electrical cables are going to come in here, and this shaft with the splines on it, that is going to be always connected to the accessory gearbox. Whoops, that's two C's. The accessory gearbox, or whether you, in any case, this is very important because in a slide or two ago, we talked about having a hot start or a hung start. If that hot start or a hung start occurs after you've let go of the starter switch, if this was like a car, a reciprocating engine starter, where if you let go of the starter switch, the starter retracts, the gears on that starter retract away from the engine. And once the engine is spinning, if you push the button back down, in a car you may have done this once or twice, and you can hear the gears grinding. And what might happen inside of the gearbox of a turbine engine, the splines, the gear teeth may break off and go into the engine. It's time to take the engine apart. The magnetic chip will come on, will rehearse many words, and you will be trying to figure out how you're going to explain what you did to the box. The nice thing with electrical starter generators is that shaft with the teeth in it, they don't retract, they don't go in and out. When you teeth go into the gearbox, and it's always engaged, it's always connected. So unlike a piston-powered airplane engine, and unlike your piston-powered car, if you let go of the starter switch on an electric starter motor on an engine, the starter is the starter, because correction, starter motor gone, the shaft is still engaged. So if you had a hot start, say you had a hot start, the engine gets up to 20%, you turn on the ignition, it gets turned on, the fuel nozzles get turned on, the fuel catches on fire, it keeps accelerating, it gets to 40%, you let go of the starter switch, it gets up to 42, 43, but now it slows down and it doesn't speed up to 50% idle. Wow, what is this? It doesn't get all the way up to idle. It slows down and it stays at 42%, and it doesn't go all the way up to 50. So you have a start, a hung start. So what's the procedure for a hung start? Fuel nozzles off and motor the engine if possible. And in this case, if it's a DC starter motor, I'm going to ask you this at the time. If it's a DC starter motor, if you let go of the starter switch and you're not going to break anything, yeah, you can go ahead and push the back switch down because it's still connected. So that's if you have a starter generator, if you have a hung start occurs after you've let go of the starter switch, you can reapply the starter switch. Yay. Okay, I think that's yay. The test question would be something like, everyone except White gets this correct. To answer your question, it would be, you have a start on a turbine engine that's started by a DC starter generator. If you let go of the starter switch and you have a hung start, is it acceptable to push the starter switch back down even though you had already let go of it? Is that working? I've written these test questions before. So. No, I didn't. I don't have a schematic for that. And so it would take some interesting use. We found yesterday with the APU, we turned on the master switch. Correction, we left the master switch off, but we had electrical power going to the APU. So we had power out of the ground power unit, and it was going to that APU. But the master switch on the APU was off, demonstrating how to use the start run. And when I went to start, the starter kicked in and it started up. It started to start up. It's like, ah. So I would never have wired it that way. When it says master switch, that's like the masters of the universe. I want everything under my control, and I want people to. I think it is not wired the way I want. That is correct. Okay. So there's the question. Well, there's a different way to ask that question. Are DC starter generators, is the DC starter generator always connected to the gearbox engine? All right, is it? Yes, okay. Why is that a wonderful thing? See, here's another way to ask the same question. Well, it makes it so that once the engine spins up, you can turn the starter into a generator. Why else would it be wonderful that the starter generator is in the gearbox? Yes, you're right. We're not going to have teeth engaging. But we just talked about it 3 minutes ago. Right, and I'm going to try. I would accept it on the test, but I'm not going to use the word re-engage because technically it's still engaged. We can reapply power to the starter motor, and it will not damage anything. There, Wyatt, I've given you 2 different ways to ask that question. I'm sure I'll come up with a third way that you will not understand what I'm saying. Starter generators are an energy conversion device. They accept large amounts of electrical power. It may be 28 volts, which doesn't sound too much, but what if it's 700 amps? Let's see, just for fun, 28 volts. Let's see, watts equals volts times amps. 28 volts times 700 amps. Anybody got a calculator? 2.5 times 7 is about 2,000. Is that what, about 2,000 or so? 3,000? 19,000? Or 1,900? 19,000. Okay. If we divide that by 746, that'll give us horsepower. So that's about 25 horsepower? Is that what it is? Is 19,000 divided? Because there's 740. I'm not going to ask you to do this math on the test, so don't flip out. There's 746 watts in horsepower. So 7 goes into 19, a little over 2, close to 3. Put some more zeros on it. So like 26 horsepower. Yeah, now that's a starter motor you can be proud of. You can take that home and show your mom. Look, Mom, I got a starter generator. It puts out 28.6 horsepower. Well, you don't have to show your mom if you don't want to. That's okay. All right, so if it has a very high current flow during start, then what happens to the temperature of the starter motor? It's going to go up. That starter motor's going to get hot. So I'm going to ask you a question about duty cycle. Duty cycle is talking about how much can I operate this starter generator, this electric power starter generator. How much can I operate it? How much do I have to wait for it to cool down so I don't melt the inside of it? So I'm going to give you a very typical, a very generic set of numbers, which every starter generator duty cycle is a little different, but it might look something like this. It might be 30 seconds, can be on, and then you have to wait 30 seconds off, and then 30 seconds on, 30 seconds, oops, and then 30 minutes off. So it's going to say you can operate that starter motor 2 or 3 times, and then you're going to have to wait 10 minutes, 20 minutes, 30 minutes. So every electrical starter generator is going to be a little different, the duty cycle. The duty cycle is how long can you operate the starter motor, and then how long do you have to wait before you can do it again. And so if you're going to go start a turbine engine and it's got a starter generator on it, you need to look that up. So when you take that aircraft outside and you're going to run the engine, you know what the starter duty cycle is, and you don't melt the starter motor, because then someone will ask you some interesting questions. When I say interesting, I'm being sarcastic. Any questions about duty cycle? All right, let's keep going. I have many, many more things to tell you. All right, so we just covered starter generators. Now we're going to talk a bit more about pneumatic starters. And I'm not going to ask you, if I asked you about what starters are on what kind of aircraft, you would say starter generators are found on small turbine engines. Starter generators are found on aircraft where the primary electrical system is 28 volts. And you don't have to write this part down, but what aircraft have primarily 28 volt DC? You have to write the small turboprops like a PT6, small turbine-powered helicopters that out in the warehouse. These generator on it. PT6 DC starter generator. They're installed on air. One of the reasons the engine's small enough, the starter generator, and the battery weigh less, and the aircraft power system is primarily 28 volts DC. On the other hand, pneumatic starters, of course, pneumatic starters use high volume, high pressure air. They're going to be found on very large engines. You don't have to spell the word big O honkin' on the test. If you'd rather write the word large, that's fine with me. And you don't have to write down the following list. I'm not going to ask you this answer. Where would you? This is the way I would ask the question. Where would you find pneumatic starters? You would find pneumatic starters on large turbine engines, and you would find pneumatic starters on aircraft that have alternating current, AC, as their primary electrical power. I think I have that. There it is. Ta-da! So that's where you would find pneumatic starters. The vast majority of turbofans are big enough that the weight of an APU and a pneumatic starter is less than the weight of electric starter motors and batteries. But I have seen small turbofans on some small biz jets that used electric starter motors, and they didn't have an APU on board. So you can't just say turbofans. It's big turbofans. So if the primary power system on transport category jets, I'm not going to ask you these four, when I say transport category, we're talking airliners, big biz jets, big turbine helicopters, big turboprops. All those aircraft use 400 volts AC, alternating current, as the primary power system on the aircraft. Then it's going to have an APU that provides pneumatic power going through stainless steel ducting out to the engines to pneumatic engine starters. Because the weight of the APU and the weight of all the pneumatic starters and the weight of those stainless steel ducts are less than the weight of having enough batteries and very, very, very heavy electric starter motors. Let's just say for fun, I'm going to make up some numbers. Let's say it's a Boeing 777. Those engines put out about 100,000 pounds of thrust. I'm going to make up a number and say that the pneumatic starter on it weighs 100 pounds. What if the starter that you had to put onto it 500 pounds each engine? So if we put pneumatic starters on it, we say 400 on each. That's 800 pounds. Well, what if our APU only weighs 200 pounds? And we're running most of that pneumatic ducting around the airplane anyway. We're still saving several hundred pounds. And wait, we got to have an APU anyway, because we want to be able to have pneumatic power on that APU to run a generator, so when you have electrical power, because everybody in first class always wants a margarita before the engines start. So they got to be able to spin a blender in first class. So you need electrical power on the ground, so you need the APU anyway. You need to be able to run the air conditioning heating system, so you need the APU on the ground anyway. So really, you can even throw out the weight of the APU. So hopefully you can see why big O honkin' jets, big turboprops, big business jets, big turbine helicopters, they're going to have AC systems, they're going to have APUs, and they're going to have pneumatic starters on their engines. Did I lose anybody there? All right, a pneumatic starter. I'll show you a picture of it here. I'm pretty sure I have a picture. Show me a picture. I want to see a picture. Now I feel bad. Maybe not that bad. Where did it go? Maybe it's on the next slide. No. I guess I'm going to have to draw a picture. Yeah, I get to draw pictures. Okay, maybe you don't like it, but I like drawing pictures. So a pneumatic starter is literally just a turbine wheel. So we have a turbine, and you're going to have turbine inlet guide vanes. So essentially these are the stationary blades. And then you got one set of rotating blades. And this is just like a single stage of a turbine engine, except that there's no combustion chamber. We're going to take this output shaft and we're going to run it into a gear reduction box. And then that is going to go into the accessory section of a big old honking engine that I can't even draw how big it is. So literally, you're going to take pneumatic air or high volume, high pressure air. It's going to be hot, but we don't really care if it's hot. And you're going to run the air through this turbine wheel. And then the power extracted by this turbine is going to spin all the gears around in this gear reduction. But this thing right here, you know, it may be spinning 20,000 or 40,000 RPMs. You don't have to write that down, but it's going to be a really high RPM. And at first, this gearbox going in here, we need it a lot less than 20 or 40,000. So there's going to be a reduction in RPM. And that's going to run the accessory section of the engine, and it's going to have gears in it, and then it's going to supply its power to the shaft inside of the engine. So a turbine wheel and the stationary blades and this gearbox don't have to weigh that much. This turbine section here, this one stage of turbine energy extraction doesn't have to weigh that much. The gearbox weighs more than this turbine does. And remember, the point of a turbine is really just to extract energy from high velocity gases going past it. Of course, you need high velocity and high volume. So did I lose anybody about how a pneumatic starter works? I do have some more pictures, I know, somewhere. Question? Okay, so there it is. The aircraft is going to be a very large engine, and the primary power system is going to be 400 volts alternating current. Just explain the fact that it's really just a small turbine wheel that extracts energy, and it gears it down, and that goes into the accessory section. And you can get this high velocity, high volume air from 3 places. That'd be a great test question. Where can you get pneumatic power to run a pneumatic starter? Well, you can run it off of the APU aircraft. You start that up with with a battery. Now the APU is running in the tail, and it fills the pneumatic system full of air. So now you can start all your engines off APU if you want to. And that's a very, 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 very common way to do it. Or you could have a ground power unit. You could have a ground, really just an APU on wheels, and it's a hose, like a 3 or 4 foot diameter hose, and you hook it into the pneumatic system of the airplane, and then the pneumatic system has high volume, high pressure air, and that can be spin. After you get one engine started, can you take bleed air off the compressor off of that main engine or the pneumatic system on the airplane? Well, of course you can, because you're going to do that all day long when the engine's running on normal operations. So you can actually disconnect the ground power unit or turn off the APU, and now use the one engine you got started to provide pneumatic power to start all the rest of the engines, or any combination thereof. The majority of the time, if you're looking at transport category jets, big old turboprops, and big business jets, running. If I ever sat in it, the air conditioning is on. People in first class are getting margaritas, and they push the airplane back from the gate. They don't have a ground power unit hooked up, and the main engines aren't running yet. They push it back, and then they start the main engines. Where do the main engines come from? The APU. And it's faster to not worry about anything and just leave the APU running and start all the engines while the APU is still running. That's typical. Same thing for big business jets. So we already covered the fact in pneumatic starters, if you take into account the weight even of the APU, but the weight of pneumatic starters, for the same power, it's less weight than big, gigantic. And the batteries that you would have to have. Wow. I wish I hadn't erased all that stuff. You know what? I'm going to go to another picture because I know I got a picture in here somewhere. Yeah, let's use this one. So here is one type of pneumatic starter. We're going to look at it here shortly. And you'll notice in this case, although the picture I drew, no, it's not the one I was looking for. It's not the droids I was looking for either. But this right here is a radial inflow turbine. So if air goes in here and then comes out here, this is a turbine wheel. So can you have an axial flow turbine? Can you have a radial inflow turbine? Is that what Mr. Asman called them, radial inflow turbines? Not the compressor. A centrifugal turbine? Okay, that works great. All right. The shaft of this goes into gear reduction, and then it goes out here. The problem is that while you're starting the engine, this thing has to those gear teeth, that spline, it gets inserted in the gearbox. Then after you let go of the starter motor at 40% RPM, it's spring loaded. It retracts back into the starter motor because you don't want this pneumatic starter spinning when the engine is at 100% power. This thing hits red line at around that 40%. When the engine's at around 40, this thing is coming up on red line. So if you left it engaged, this would spin more than twice as fast as it was designed for, and it would come flying apart. So you have to disengage. Literally, that shaft with the gears has to disengage and get pulled out, get retracted out of that gearbox. So let's try that same example. You're starting an engine. Start spooling it at 20%. The fuel nozzles come on. Correction, the ignition comes on, then the fuel nozzles come on. You're monitoring the EGT. It comes up there. You might be checking the oil pressure. 40%, you turn off you let go of the starter switch. It accelerates from 40 and it goes to about 42. And it hangs up. Continue. What's happening? You get a hung start. So, number one step is fuel nozzle. Motor the engine, if possible, and this is why we have to use that word, the pneumatic starter. And those gear teeth have been go into the engine. What's happening to the pneumatic starter? When you let go of the switch, towards zero. What happens is if your car engine is the starter, it's going to mess up your teeth, except in your car, it's going to grind. You're going to go, and you let go. And those teeth are built pretty strong because people are, and so they build those teeth extra strong. But if you do this with a pneumatic starter, and that teeth try to go in there, it's going to break off teeth. They're going to fall down into the bottom of the gearbox. You're going to have a magnetic chip detector light come on, and the teeth are all going to break off, and the starter won't engage to the main engine anyway. So now, not only did you have a hung start to deal with, now you're going to have to tell somebody how come you broke off all the teeth, and now there's metal in the gearbox, and you can't go flying until somebody takes the gearbox off and gets all that metal out of there. So this is really critical, which is why I'm going to ask you on the test. If you're using a pneumatic starter, and for any reason you have let go of the starter motor, what happens to the gear teeth on that pneumatic starter? Does it stay engaged in the end, or does it retract back to the starter when you let go of the starter? It retracts. Now, what happens to the speed of of the RPM inside? It starts slowing down towards 0. So if you've let go of that starter switch and it's a pneumatic starter, are you authorized, okay, to push the button? Why can you not push that button down? The engine is spinning, the pneumatic starter is spinning slower. If you push the button down, that shaft will go in there and all the teeth will break off and everyone will be unhappy. All right, so then the last question on here, which was on the previous test. Pneumatic starters generally, typically, don't have a duty cycle. Are we pumping a lot of electricity through a pneumatic starter? No. Is the air hot? Yeah, but we got a turbine section. You think somebody designed, the engineer designed this turbine section to allow 400 or 600 degree Fahrenheit air to go through it? Yeah, because that's what's going to go through it if it's coming off of another engine. So you can just run it. That's why on those compressor washes on that 737, they motored it for, 3 minutes? But on the other two engines, I think they were electric starters because they only motored them for 20 or 30 seconds, William. Oh, the last word's typically no duty cycle. The question is, why is it not like DC starter generators? So why can you, so that would be one way to ask the question. Why can you push the button back down on a DC starter generator if you and the engine is extra? Why? I'm talking about duty cycle here. Pneumatic starters don't have duty cycles. Why do they not need duty cycles? Because the pneumatic starter can handle the high temperature pneumatic air indefinitely. And it will not get too hot. Which works out because these giant turbine engines, the inside parts weigh a whole lot more, have a whole lot more inertia. So we're going to not just run the starter for a few seconds, we're going to run it for 20 or 30 seconds. The APU you're going to start or have started, that thing goes from 0 to 100% based on student input somewhere between 2 and 5 seconds. You try to spin up a Pratt & Whitney PT6, it's probably going to take about 15 seconds. You start trying to spin up a 747 engine, and it's going to take 20 or 30 seconds. So you need the starter motor to be able to handle a lot of power and not get overheated. So you don't have to take any notes on this slide. I'm not going to ask you any questions off of this slide. There are cartridge starters. This is a cartridge starter, and instead of this starter right here, you can pump pneumatic air into it. You can also put a coffee can-sized container containing slow-burning gunpowder, and it will blow air, and it doesn't show the duct very well, but it'll blow air into this pneumatic, into this turbine. And you can mount this, and that gunpowder gets ignited from a switch in the cockpit electrically, igniting this gunpowder. So that way you can run out to the airplane, jump in it, and you can actually start as many engines as you want. You don't, all you battery power. You turn on the battery switch, and you turn on the fuel, you turn on the fuel valves, and you run through your start, and when you get the starter motor on, you just flip the switch, and it starts the gunpowder on going. If you ever look at a video online, it looks like it's pouring out of the side of the engine because it's dirty gunpowder. It's awesome. When I was on Nuclear Alert on B-52s, we had 8 engines. There was 2 engines in one pod, 2 engines in another, and on the other wing, 2 engines in a pod, 2 engines in another. Every other engine had a pneumatic starter with gunpowder on it. So we could run out there in case of nuclear war. The pilots could jump in the top, turn on the electrical switch, and they would start engines simultaneously. And so about 30 seconds after they sat down, if it was nuclear war, they didn't until later. So in 30 seconds, they could things running, and then they would use the bleed air off of start the next one right next to it, because now all 4 out of your 8 engines were producing pneumatic power. So now it's another minute after the pilot sat down in the you could your Air Force base with B-52s on it. So fortunately, you kissed your wife or your husband and your kids goodbye, and there'll be nuclear waste here in about 10 or 20 minutes. But gosh darn it, you can take off and fly and go nuke the godforsaken, or is it godless communists? I can never remember if they were godless communists or god-forsaken communists. In any case, the only place I've ever seen gunpowder cartridge starters are on military aircraft that you wanted to be able to start the engine, and you didn't need, all you needed was a little bit of battery power.
So, if you use that cartridge,
You have to replace it after that flight, but if it's in case of nuclear war, you're probably not going to take another flight. This is probably your last flight. Ask me how much lead shielding is in a B-52 bomber to protect the crew against gamma rays emitted by all the nuclear warheads that are going to go off during that war, within which the B-52 will fly through. Sorry, the airplane's not made of lead. There's absolutely no lead shielding protecting the crew. There is some lead shielding in the bombs. So I think cartridge starters are fun. Gas turbine starters are actually a small turbine engine, like an F-16. There's a lot of other fighter jets that have this. They literally use typically a DC starter motor, and here's a shaft, and here's a compressor, and here is one set of turbines, and here is the combustion chamber. So this is literally, this part right here is a turbojet. And then with no mechanical connection, there's an extra set of turbines out here, a power takeoff turbine, if you will, and a gear reduction, and this shaft goes into the gearbox of the engine. So all you need to get this thing started is a little bit of DC power off of a little battery. Literally, I got one right here. I mean, I don't have one. School has one. So here, I'll line it up the way it is. So you can see the intake. It's very small. That is a small intake. A turbo. It's really a turbo shaft engine. And here, this is where the turbine. This is the second set of turbines. And put on it. Put a little propeller on it. A small one person. Usually the limit on these things is after 400 engine of starts on this, it's time for an overhaul. Run for about a minute, you're going to run it. You're going to start it running for about a minute, start the engine, and you're going to shut it down. So it's not really designed to run for long periods of time. The concern with putting this on unbuilt aircraft would be that it wasn't really designed to run for tens and tens of hours. But what's the worst that'll happen? The wheel will come flying apart, supersonic shrapnel will hit me and or the airplane, I will die and kill other people nearby. It's not like that's a big deal. Yes? Nuclear B-52s, they used to paint the bottom of them white to attempt to have less heat be absorbed by it during nuclear war. But in later years, they figured out, and that was when the B-52s were going to be flying at high altitude. But in later years, in the 70s and then 80s, B-52s, their mission was changed to fly most of its combat low level. So generally what you would do in a B-52 is that you would take off and you would fly across the world at 30 to 40,000 feet. And then, so here's the bad guys. And then when you're about 1,000 to 800 nautical miles away from targets, you would launch your cruise missiles. Air-launched cruise missiles. And the ones I flew, you could have 12 of these. But only one warhead each missile. And then you would descend to low altitude, and then you would fly around where the bad guys were, and you would launch. You had 8 short-range attack missiles, and they were rocket-powered, and they would go Mach 7. It was a 2-stage solid rocket boosters. It would go Mach 7, and unclassified distances, they'd go about 50 miles. You could fly past them and launch it, and the missile would turn around. And then, of course, the fun part is, in a B-52 in the bomb bay, in the back was a rotary launcher with these 8 short-range attack missiles, like a revolver on a gun. But in the front, there was 4. You could put 4 gravity bombs in there, so you could also have 4 bombs. So let's see, 12 plus 8 plus 4 equals 24 warheads. The problem with flying around with these, the nice thing about the cruise missiles, they're going to blow up a long way away. Same thing for the short-range attack missiles, they're going to blow up a long way away. The bombs, on the other hand, let's just say for fun, I'm going to make up a number that's not classified. You're going to fly 400 feet above the ground, and you're going to be doing about 400 miles per hour, and the airplane is probably going to weigh about 400,000 pounds. The problem is with this nuke, is you're going to have to drop it out, and you don't want it to break when it hits, so you put a parachute on it. It falls down, and then it just sits there, you know, with the parachute hanging off it. People are going to walk up to it and say, "Yo, what's up?" And you're going to fly as fast as you can. Maybe we'll go 500 miles an hour. How far do you have to wait? How long do you have the timer in this bomb set for so that you can fly far enough away so when it goes off, you die soon? This is an unclassified number for training purposes. 90 seconds. I hope you all have a great weekend.